introduce what's that equation called? Somebody's equation. It's named for somebody. We're going to introduce the equation that connects the Gibbs free energy to the magnitude of the difference in potential that an ion moves through when it crosses from one species to another. That equation looks like this. Delta G is equal to N times F negative N times F times E, where this is your change in Gibbs free energy. N is the number of electrons that travel through a potential difference. F is, or this is the number of moles of electrons. F is Faraday's constant, which accounts for how much charge is on a mole of electrons. And E is the potential difference. So this is just an energy term, right? This energy term is the amount of energy that's released when essentially we talk about it as if it's a potential difference, but it's all the same thing. It's all energy that is released when charge moves closer together. Positive and negative charge move closer together, creates a lowering of energy. You take positive and negative charge, they attract to each other, push them apart, it raises energy, etc. This is all a question of how much electric potential energy gets released when an electron travels through a field. So, I kind of want to introduce this softly, connected to the thermodynamics. Say we take a system of zinc chloride. Throw it into water, and somehow this thing is incorporated into a calorimeter, and so we can measure the heat. Throw this guy in the solution, and we find out that delta H is equal to negative 233 kilojoules. Throw these ions in solution, 233 kilojoules of energy gets released into that bath. Then you do it a different way. See if I can draw it a different way. You separate these guys. And wait, am I doing this right? Sometimes I just start talking too fast. I should have shut up and thought about what I was about to say first. So we take a zinc chloride solution, and we take or zinc chloride. So we've got zinc solid and a zinc chloride solution, and we throw it in with a silver chloride solution. So you've got zinc metal in contact with silver ions. What's going to happen? What's going to happen if you take zinc metal and you stick it with Ag+? Who pulls on electrons more strongly, zinc or silver?
Zinc.
Really?
Silver.
Silver is the thing that we make jewelry out of, right? We make jewelry out of silver because silver holds on to its electrons. It doesn't tarnish. It doesn't oxidize. So if you stick a bunch of Ag plus in solution with a bunch of zinc solid, the silver is going to steal the electrons away from the zinc, right? When this happens, those electrons are going to move from a high potential to a low potential. It's going to release energy. So you do this, and you find out that 233 kilojoules of energy get released in this process. And that amount of energy, that delta H, is somehow a function of the change in the electric potential that those electrons go through and other changes that might happen in the solution. Learn to look at entropy changes in different systems, and so we can expect that some part of that delta H could include entropy terms. So we take this system, dump it all together in the same bath. You get 233 kilojoules of energy released. Then you try it a different way. Then you take the AgCl solution and you connect it via an electrode to a zinc ion or a zinc electrode. And let the current, let the electrons get pulled by the silver ions away from the zinc ions. And what you end up with is a bunch of zinc 2 plus, Cl minus in solution over here. And you end up with Ag solid, silver solid, depositing on this electrode over here. The same net effects happen. You took solid zinc, the electrons possessed by it, and you gave them to silver. And so those electrons move to the same potential as they did when you just mixed them all together. But let's say that this time you let them travel through a resistor, and you put that resistor in a calorimeter. And you measure the heat. Comes off the calorimeter. In the limit of infinite resistance, so you make this resistor just a really big R, and that means that that current has to move infinitesimally slowly through the resistor. In the limit of infinite resistance, you find out that the amount of heat dropped off here approaches negative 190 kilojoules. And the sum of the heat changes that take place in these compartments approaches negative 43 kilojoules. You notice the sum of these things is 233, right? Work is equal to force times distance. When these electrons moved through that potential, there was a force that was exerted on them, and they traveled under the influence of that force over a certain distance. And although I said that the heat, or the energy was released as heat in this process, it was released as heat because we stuck it through a resistor, and the resistor converts that energy into heat. We didn't necessarily have to make it be heat. It could have been turned into work. If this was an electric motor, that could have been work energy that was released. What we're getting at is that we made this process reversible. And when we did that, we generated the maximum amount of work available for that process. Remember when we went through the different gas cycles and we said that the process that happened reversibly did the maximum amount of work possible? Well, we made this electronic charge transfer process happen infinitesimally slow, reversibly. And so we maximized the amount of work that could be done in that process. Now, we had some other Q. We had some other amount of Q that was released in this section in the solution, and that was heat that was released as a function of like the changes in the spatial ordering of the electrons, the ions of the solution. What we're seeing is that our delta H, which is the total amount of heat released in this process, ends up being a function of two things: the entropy changes, which account for the heat that was released in those solutions, and the Gibbs free energy change, which is the amount of energy that is, in this case, in this system, that is was expended as reversible work. What's delta S for a reversible process? What's the integral of dq over t for a reversible process? What's that? Not over a closed path, it's zero. But integral dq over t is delta S. Right? That's our entropy. And so we conducted this process reversibly, and we saw that there was an amount of work done, and there was an amount of heat that was released that was less than that amount of work. The heat that was released ends up being a function of entropy effects. And so this is, if you guys remember, anytime you're converting energy from one form into another, it's going to happen spontaneously. You have to release some amount of energy as heat. And so the heat that we observed being released in the solutions was due to entropy changes, and the heat that was released over the resistor was a function of the work that was done, the electrical work that was done in transporting those charges. All right, it's time to go. So we'll pick up there when we